Let's discuss a question on conduction heat transfer. So a cylinder of radius r made of thermal conductivity K1 is surrounded by a cylindrical shell of inner radius r and outer cylinder 2r. So let's draw that. So you have a cylinder which is basically of r, and then on the top of that you have a cylindrical shell which the inner exactly fits with the outer of this solid cylinder, and the outer radius is 2r. So if you look at the cross section, yeah, so this is r and this is 2r. Okay, and the thermal this is material K1 and this is material K2. Thermal conductivity, different material, different conductivity. The two ends of the combined system are maintained at different temperatures. So you have this phase, let's say, maintained at T1, and this phase maintained at T2, and there is no loss of heat across. So across in this direction heat is not there. Okay, so heat flows only in this directions. In this direction it is not allowed. Okay, because it is given, and at steady state the effective thermal conductivity. So remember that the heat flows in this direction. Now you have two options. Let's say if T1 is, let's say begin without loss of generality, you can assume that T1 is more than T2. Okay, either way, T1 or T2. So when T1 is more than T2, the heat will be flowing in this direction as given by this symbol Q, and it has two options. Either it can choose material 1 or it can choose material 2. So this is basically a thermal, it's a parallel thermal circuit. You have Q which splits into Q1 and Q2, and then so it's a parallel thermal circuit. So I can write Q as Q1 plus Q2, heat flux as some heat going into one cylinder and the other going into Q2. Now heat flowing through, so this is just, let's say if you take a cylinder, in the inside cylinder you have Q1 flowing it. Now if you use a slab, this is just like a slab but with a this is just an actual heat flow in a cylinder. So it is just similar to a heat conduction in a slab, where you can write heat flux, steady state heat flux as delta T by L, Ka delta T by L. That is what you can write for a heat conduction flowing in a slab. So I'll just write only delta T at the top and L by Ka at the bottom. So for Q1 it will be delta T by K1 into A1. Sorry, there is L. Yeah, L by, let's write it in a better way. So delta T by L by Ka, K1 A1. Okay, and for the outer cylindrical shell also it's just like similar to this way, but only thing is area of cross section is different, but heat is flowing in an actual direction. So length will be same, K2 and A2, and what is asked basically is effective thermal conductivity. So effective is, what it means is that if I happen to replace this entire thing with one cylinder, okay, and the area of cross section being the same, everything being the same, but if I happen to replace this with the one material with the same temperatures, inlet, outlet, and area of cross section same, then what is the thermal conductivity for the same heat flow? So in that way, how do I write K is net Q is delta T by L by K equivalent into total area. So this is my equation, and now what I do is, okay, so what I'll be doing here is, now I'll be just okay, so the delta T's gets cancelled out, and the delta T's gets cancelled out. So effectively what I'll get is K equivalent into A is K1 A1 plus K2 A2. So this is the equation which I get it. Now I need to substitute for A1 and A2. Now if you just come back here, A1 is the area of cross section of the inner cylinder, which is of radius r, so pi r square, and A2 is this. So the total radius is 2r, so pi into 2r whole square minus the inner solid will give you the cross section of the cylindrical cell, which is A2. So let's substitute it here. Okay, so let me just so what I get now is, let me just begin with, yeah, let me just stop this. And so now what I got was, in the last thing was, K equivalent was K1 A1 plus K2 A2 by A. So A1, as you know, because I have drawn that, so it is pi r square, and A2 was the total. Let me draw it here, because the total was 2r and the inside was only r. So A2 would be pi 2r whole square is the total cylindrical cross section minus pi r whole square, and your A is basically A is A1 plus A2, which is nothing but pi into 2r whole square. So if I substitute everything in this equation, what I get is K equivalent is K1 into pi r square plus K2 into, this is 2r square, so it becomes 3 pi r square by pi 4r square. So we get K1 plus 3 K2 by 4. So this is the effective thermal conductivity, and the option for this is, let's look at the options. Options for this is K1 plus 3 K2 P. This is a simple problem, and the basic thing is that most of people may be confused with, they may think this is cylindrical flow. They may not think that it's cylindrical, I mean actual flow. They may think it's across the cylinder, and they can apply the formula with that ln r2 by r1. So it's a simple problem. Yeah, thank you.